Welcome everybody to our first event organized by the Women in Engineering Affinity Group Polito. I am Antonia Silvestri, PhD student in Electronic Engineering and chair of the Women in Engineering Affinity Group of Politecnico of Turin, and today I have the pleasure of welcoming you at the first IEEE WEA Distinguished Lecture at Politecnico of Turin. I am glad to introduce to you the Dr. Engineer Sanaz Mostaghim, full professor of computer science, chair of computational intelligence, founder and head of a Woman Lab at the Faculty of Computer Science at Otto von Guericke University, Magdeburg in Germany. Her research interests focus on multimedia decision-making, collective learning, and their applications in robotics and science. Professor Sanaz is a deputy chair of informatics Germany and a member of an advisory board on digitalization of the Ministry of Economy, Science and Digitalization of State of Saxony-Anhalt in Germany. She's an active member of IEEE Computers Intelligence Society, CIS, and the CIS Administration Committee. She is an associate editor of IEEE Transaction on Artificial Intelligence and Evolutionary Computation and a member of the editorial board of several international journals on robotics and artificial intelligence. Today, Professor Sanaz Mostaghim will present the talk entitled MultiCriteria DecisionMaking Algorithms from Individual to Collective Autonomous Decision-Making. After the talk, there will be time for questions, and I invite all the people who want to ask questions to comment on the YouTube video. We will read your comments and ask the question for you after the talk. Please, Professor Sanaz, the floor is yours.
Thank you, dear Antonia. I try to share my screen. And hello, everyone. Welcome to my talk. I think you can see now my screen. Well, yeah, so thanks, Antonia, for introducing me. I just want to introduce now where I come from, and maybe you are interested to know where Magdeburg is. So this is a map of Germany, and probably some of you know Munich. You call it in Italian Monaco, and there is Frankfurt here. Berlin is here, and Magdeburg is only 1 hour drive to Berlin. So this is where I'm located. And you might ask, who is this guy that you saw in the beginning, the face and also the logo. I just want to introduce also where I am, at which university I am. The name is Otto von Guericke, and Otto von Guericke is someone who is very famous for engineers. He invented basically vacuum, and it was 1654 where he did this experiment. The experiment is like he put 4 horses one side, 4 horses the other side, and he put two hemispheres, pulled the air out, and these horses were not able to take these hemispheres apart from each other. And this is the origin of vacuum, and vacuum is used in almost every engineering system that we have in the cars, in fabrics, everywhere. And he basically showed that a void, a vacuum that is nothing, has so much power. And today we still do this experiment. So if you're interested to come and visit me, probably after this talk, you will be interested to come and visit my lab. All of you are welcome to come here. But we do this experiment once in a year. You see here a picture where people bring the horses. The horses are so excited when they are part of this experiment. They don't understand what they have to do actually. And here you see the hemispheres, the 2 sizes of the hemispheres, and people gather their children and they all look at the science and how Otto von Guericke, so many years ago, he tried to do this sort of work. So now, but to the content of my talk, I want to talk about multi-criteria decision-making. Decision-making is one of the important topics that we all encounter every day. When we get up in the morning, we are sort of need to decide what to do, how to go to university, which way to take to the university, and so on. And in my talk, of course, I don't want to talk about human decision making, even if it is also my sort of my expertise in that area. I want to talk about decision making at runtime for autonomous systems or artificial intelligence agents. And then I want to talk a little bit about collective versus individual decision making. What happens if you have many cars, many autonomous driving cars, or many agents, a swarm of agents, if they can make a better decision than an individual, and how we can influence in decision making for individuals or collectives. And at the end, I want to talk a little bit about ethics in AI and decision making. If you have a car that is able to make a decision and is doing it on its own, who would be then responsible for a bad decision? So let me talk about first what is multi-criteria decision making. If you have multi-criteria decision making, well, basically, if you have anything to make a decision about, it means that you have several alternatives, and you can't, unfortunately, take all of them. You have to decide for one of them. So it means you have conflict. In engineering, electrical engineering, when I was studying engineering, I know that we were talking about trade-offs. And it is about something which we call it multi-objective optimization problem. What is the optimization, multi-objective optimization problem? It's very simple. You have several functions or objectives, and you want to optimize all of them at the same time. And but the important aspect is that they are all in conflict with each other. So an example is going home from work, and these are the options that I actually have when I come from home to work. You see, I have 4 options. And if I take the car, it costs me a lot because I need to have a car. It takes me 6 minutes. It's a very short time. If I take the tram, it takes 32 minutes, a bike 10 minutes, and walking, which is the cheapest way. Probably I need to have some good shoes for that. It will be 32 minutes. So if I put these options together, you see that I have two criteria. One is cost, the other is time. And if I put all these options, you can see here that some of these options, sorry, my computer is turning to an update. Anyway, I hope that you can see now. So now if you see all these options, you see that, for example, the tram is sort of dominated. So it takes me exactly the same time as walking, but it costs me some money because I have to buy a ticket to come to university. So then the alternatives that I can make a decision from are these ones, either walking, taking the bike, or the car. And actually a decision maker, which is me, has to select one of these alternatives. First of all, we have to find all these alternatives. That's why you have to do an optimization, which I'm not going to talk about it in this talk, how we do the optimization to find all the possible alternatives. For this very simple example, it's just easy to find them. Another example, which is probably an example you will see in future, is what about if there is an autonomous driving car and standing in front of a roundabout, and it has 2 criteria. One is waiting time, and the other one is risk. If it wants to go into the roundabout. So here is a video. So basically, what happens is that this car is looking at his options, and the options in this case are very, very simple. Like these are the options. If he goes this time step, or this time step, or this time step, so he looks into the future and finds some options that you can see here, how much time he has to wait for which option, and how much are the risks. And exactly like the other example, you can take those, put those options that are not so good, they are dominated by the others, away, and then you have basically 3 options that you can select from. And if you want to see how it is working, basically the agent is trying to make some certain decisions. And this is actually, the agents are doing it at runtime. And you can see here there was a little mistake. One of them was too risky to take a decision. Anyway, so what happens is that you have an optimization problem. So this is a minimization problem of two objectives. One of them is the time, waiting time, and the other one is acceptable risk. So, and here the decision maker is an autonomous driving car. It's not the human being anymore. It's the car, it's the programmer, it's me that I'm giving the ability to the car to make a decision. And that's why I said that ethics is very important. I will talk about that later. In mathematical generic form, you can say, okay, imagine that we have m functions, m objectives. And the examples I showed you, they were very, very simple. But if you could also say, okay, each of these functions has also certain variables. And so you have a space of x and then f of x, and you have m of them, and you want to optimize all of them. So for example, here we are minimizing all of them without loss of generality. You can also define some constraints for your decision variables. This x is a decision variable, and there could be n-dimensional space. So you can make the problem really difficult. And in my research group, we work on all these aspects. What happens if you have many of these objectives? What happens if you have many of these decision variables? And so on. And one thing you can also see, which you already saw in the actually other examples, what happens if we plot these functions. So in here I show two functions, f1 and f2, in terms of each other, which I showed like by cost and time, or time and risk. This is the so-called objective space where we make the decision in multi-criteria decision making. And another example which could help you to understand what happens in optimization is this example. You have two functions, x to the power of 2 and x minus 1 to the power of 2, and you want to optimize them at the same time. This is an academic toy example, but you can see here, if I want to optimize f1, the minimum is 0. And if I want to minimize f2, the minimum here is somewhere 1. But if I want to optimize both of them at the same time, 0 is not anymore the optimum of f2, and 1 is not anymore optimum of f1. So basically, I don't have one single solution to this problem. I have a set of solutions which are identified here between 0 and 1. And these are the solutions that are better than any other solution that are located somewhere else. Let's say if you take a solution -2, this solution -2 has f1 and f2 much larger than those solutions that are between 0 and 1. You can also plot these two. I used MATLAB actually to plot these two functions in terms of each other. So these are exactly these positions. Every solution here, which has f1 and f2, is now mapped into this space, which we call it objective space, where we make our decision later. And you can see the optimal solutions, which were between 0 and 1, are located now here. These are the better ones, and the rest of them who are here, they are the solutions which are dominated, like the example I showed you, like the tramp one, or the other one with the autonomous driving car, the options that they were not really interesting. So the thing is, we find a set of alternatives. These are optimal alternatives. And for your information, if you want to know how I find these alternatives for very complicated problems, not such problems, these are really toy examples, we use evolutionary algorithms or other approaches where you can basically try to find as many as possible alternatives which are located here. They should have a very well spread. They should be converged. So we talk about convergence and diversity and all the aspects there. And now, if you want to do decision making, something happens. What is the multi-criteria decision making? Basically, it's the same. Multi-criteria decision making is an optimization problem. So you have several functions. You want to optimize them at the same time, the same as optimization. Now we know the solution is a set of optimal solutions, but you want to select one solution at the end. So this is the decision making part of it. And if you have a decision maker, like you want to buy a car, or if you have a human being as a decision maker, it's easy. You give the alternatives, and the human being is going to make a decision. The difficulty comes when we have a machine which has to make a decision, or maybe the human being cannot define, it doesn't know how to do. Actually, decision making is a science in itself, and people are working on that since 1700 something. So it's a quite old discipline where people try to work on decision support systems and visualize the solutions, help even the human decision maker to make a good decision. Even politicians, for example, nowadays, they have to make decisions like in Corona times, how to deal with the situation. There are so many conflicts, there are so many decision makers, this is really, really complex problem to solve. Also, providing several alternatives is good because it gives confidence to the decision maker. Even if you know which car you want to buy, still it is good to have several options, and then you say, okay, I know these are the options. I didn't want to buy, for example, that very expensive Ferrari, but at least I want to have it on my set of alternatives that I can at least compare with each other. And that is also for critical applications, like let's say cancer treatment plan. If you make an optimization plan, so if you give several alternatives, people who decide for one of these alternatives, they are more confident, they feel better than just giving them one optimal solution. So there are lots of benefits in providing several optimal solutions and optimal alternatives at the end of the optimization. And then the decision maker, the difficulty is that the decision maker has to make a decision. Now, you are all engineers and you might tell me, oh, this is nothing. We are doing that for quite a long time. We do it so much. We can, for example, we can use weights. For example, here is one of those classical preference-based decision-making approaches. You can use weights or constraints. For example, the decision maker selects his preference as a weight. For example, says function 1, oh, sorry, here should be 2, or n. So you have several weight values, and you multiply the function values of each of your alternatives by that weight, and then you try to select, for example, the minimum of that. I'll show you an example on that on the next slide. The only problem is that the decision maker doesn't have the weights or the preferences. It's very difficult. It's too complicated for a human being to define the weights, actually. And might not, sometimes people do not have any preferences. They don't know what to look for, actually. And sometimes you have too many alternatives. So the examples I show you, because of visualization purposes, I only show two objectives, but usually we can have like many of them. Even by 3 or 4, the decision maker doesn't know what preferences he should give. So let's look here as an example. Let's say we have a maximization problem, and let's say we want to buy a car, and we have these alternatives, car number 1, and the objectives we define are beauty, speed, comfort, and size, and we want to maximize all of them. So let's imagine that we have 3 alternatives. There are optimal alternatives. And so the first alternative, the car number A, called A, is not beautiful, but it has the highest speed, comfort, and size. The number B is middle in all of them. And C is the most beautiful one, but is rubbish in the other objectives. Now, the decision maker, let's say someone says, gives a weight, and it gives a weight, for example, the highest weight to the beauty. It could be a woman, probably, and doesn't care about the speed, comfort, or size. So it says, okay, the sum of the weights should be equal to 1. So I give the highest weight I have to the beauty, and the rest of them equal to each other, but much lower. And now if you apply this weighted approach, which is a typical approach that we use in engineering, then you see what we will end up is that the result is you basically multiply this with the first alternative and make a sum of them. You will see that the first alternative, which is the worst one in terms of beauty, gets the largest value. It means that you provide to the decision maker a solution which is not desired by that preference, by that decision maker. The decision maker will be probably very unhappy after doing this weighted sum approach. Probably would look like this. So it means that we should look for different alternatives, and it's very, very difficult to look for those alternatives and find a way. So basically, one thing we could do is that we could change decision policy, and it's very challenging to work on that actually when we have autonomous systems. So, and that's why I want to talk about decision making at runtime. So what happens if an agent is in the middle of a runtime and has to make a decision, like an autonomous driving car, or an artificial agent, for example, an agent in computer games. I don't know if you play computer games, but if you, for example, play Unreal Tournament, you have an agent who is going into an environment and has to permanently make a decision. And there are many challenges involved there. So here is a picture I show you. This is the cat and mouse, and this, I like it a lot because you see that you have two systems at runtime, and both of them want to basically, the mouse wants to survive and the cat wants to catch the mouse. So both of them are in critical time. So you don't have time. For example, the mouse doesn't have time to run an optimization algorithm to find an option. It has to find some good alternatives. And usually in technical systems like driving, autonomous driving cars, in robotics, computer games, like in Unreal Tournament, you have very limited time to take an action. To find an action and take it, it's about 40 milliseconds. That, for example, in a computer game, it is like you can do it without any delays in the game, and it's actually not visible to the others. So also the other example is the example that I talked about, the autonomous driving car. That is also the case. I mean, if you look here, they have to arrive here and make a decision. They cannot wait long, maybe a little bit longer than mouse and cat, but not much longer. So, and the other problem we have in such systems is that they are at runtime. What does that mean? It means that an action that they take now will influence all the other upcoming actions. Like in a computer game, you know, if you play chess, one wrong action will destroy everything to the end. Then what else do we have is that we can't actually plan in advance because we don't know the features coming in future. For example, the environment, we don't know how it could be, or the obstacles, dynamics, the other agents. In computer games, you can even consider that you don't know the opponent, how the opponent is going to play. So it's very difficult to make a decision, and then, yeah, so you have to consider the consequences coming there. And then here there are two questions to answer, two research directions actually to have. One of them is, can we make decisions at runtime, and how can we do that? It's a simple one, actually. There are not much options to do there. And the other one is, can we learn to change a decision at runtime? So like here, a cat and mouse, if the mouse is going through the loop for several times, if it is possible that the mouse comes out of the loop and goes somewhere else, is it possible to make a change in the decision and learn it as well? So these are the research questions that are very, very interesting. And I want to show you some sort of results. I don't want to take much time. I know that probably I can't go into the details at this stage because the background probably is not given. So here I show you an example how decision making works. I want to show you what happens in the brain of an agent when it is doing a decision making. But a brain means just how the decision making is working, not the real brain, of course. So imagine we have this agent here. This agent has to pick the point of interest, which is in red, or a point of interest which is in green. I will run the video in a while and you will see that. He has to always, so every time it's moving, he's looking all the directions around itself. For example, it can go straight ahead, it can change the angle. And we have 16 directions to select from. And then for each direction, it's selecting if it is going towards, if it is close, getting the distance to the point of interest is minimizing, and the distance to the danger. And danger are these three static points, they are not moving. And it basically doesn't want to go in that direction because these are obstacles, very dangerous obstacles or mines or whatever you can think in a computer game, and it should avoid them. So one thing you can see here is the objective space where he is doing the decision making. And you can see the red part here is showing the danger, which we go to the negative part of it. So we are minimizing this direction. And this one is showing the distance towards the point of interest, and we are minimizing both. And you can see here the alternatives. Of course, the alternatives change by time. And it has to select a very fast how this would work. I really hope that the video is working, and now you see how it is moving. So I have now set a very nice setting. Here the agent is grabbing the point of interest and is very smoothly, very nicely going through the obstacles, and is having actually very intelligent behavior. Of course, I have given this intelligent behavior to him by setting here the settings. Now I changed the settings so that it's a video, actually I'm not doing it online now, but I changed the settings so that it is now not making very it's making very conservative decisions, so it's not making risky decisions. Now I change it, and you see that it is now making risky decisions. So see, it's going through the obstacles. So it means that I, as a programmer, I can actually give the ability, give a character, a behavior to the agent to make a decision. Now the question is, if that agent can learn that by itself, can change its behavior over the time and during the runtime. This is the interesting part of the research that we can have. And so this is actually written here. The challenge is to define, learn, or change the decision policy, which are here the weights that I have just simply changed. Even if the weighting sum approach is not a good one, imagine that if we would take that how it would work, how we can change it, and how we can adapt ourselves to the environment. For that, I want to talk about an example and also an approach, which is called Monte Carlo research. I don't know if you know that, but this is the approach that was actually used in the computer game AlphaGo, which won against the human player a few years ago from Google DeepMind. They used deep learning and Monte Carlo research. What I am trying to do here is to use it for multi-objective decision making. So it's something different, which we actually proposed with one of my people here, Diego. We are still working on that, so there are certain papers coming in out. And so what you see here is the traveling salesman problem, which is a toy example of computer scientists. And we made a game out of that. So not me, but they made a game out of that. And there's a space shuttle who has to move in this environment, or let it run. And it has a certain physical constraints in movements. And it has to gather the points, point of interest, which are shown in blue. And the environment is very tricky. So it's, for example, going over the lava stone, and then it is going through the bouncing area. It's very difficult to move. In the computer science example for traveling salesman problem, we don't consider that. So we only see the points that we want to visit, and then the agent is going to find a sequence with how it would go and visit that. But in this game, it is not possible. So if you plan, so if you have a predefined plan, it's not going to work. And this is what we are also doing is we have 3 objectives to optimize at the same time. So we are optimizing time, amount of fuel consumption, which is basically written here down there, and damage. So if you go over the red lines here, this is a fire in the environment, so you will get a lot of damage. And of course, you want to gather as many points as possible in the game. So, and you have basically pre-planning and predefined decision policy. Both of them don't work. So we cannot define a weight vector, which I did in the last slide. It is not going to work in this case. And you can see here an example, a very simple example. It's not like this, so it's this is more complicated. But here, let's say if we would have had this sequence of cities or points to go, like the blue points here, the perfect TSP solver is traveling salesman problem solver, which is, there are many of them, even commercial ones, would give us a solution like this, which is very natural to all of us, right? So this would be the best, let's say, way to go. If you let this space shuttle to go, it has some difficult, it has some physical constraints, so it cannot always hit all of the points, and the total time it needs is 1040. So now if you run it with the approach that I will explain to you, it will change this, so it will not be as efficient as it would be here. This is very fast. In this case, he has to go twice the way. But if you let it run in the computer, you see that how fast it can go, and the time is almost half the time that a perfect predefined planner would offer us. So now one thing we do is that we use this multicolored research, and you can see some of the results. Basically, now what I'm interested is in the weight approach. So we have three objectives: time, fuel, and damage. And if we tell the agent to always optimize the time, it will probably find this option. If you tell it you always optimize the fuel, it will opt the solutions that it will find, they look like this. And this is for the third objective. Now we let it adopt its weight vector. So at first it will only optimize the third objective, which is the damage. In the next time step, it optimizes the preferences, so that he has always many options, but the options it takes, they are based on these weight vectors. And you see here, if we do that, we will see all of, in terms of all of them, it is better than the options that he was doing for each of the objectives separately. So now if you, that was for one of the maps. Of course, you might say, okay, now you change the map, it could be, it's different. And we tried on many maps, and we gave this ability to change decision policy over and over. And you can see that in all of these cases, different maps with different difficulties, it's actually doing very well. In my research, I'm also interested in applying that in robotics. So we do also decision making in robotics. Of course, in robotics, we do a little bit simpler behavior. We are not that far like in real in computer games or in theory. But you can see here also a robot in my lab which is flying. It's a fully autonomous robot which is flying indoor without any control from outside. And is basically avoiding obstacles, which one of them is a dynamic one, which is one of my PhD students, which is following it, and is actually doing quite well in making decisions, which direction to go. Basically, the decision is where to go, which direction, and it is quite well. Another example is now these characters that I defined in the computer game. I showed you there were different characters, for example, conservative, or a character which is very aggressive in that sense. You can see here what you see is one of the flying robots. It's actually VREP, one of the physics-based simulations. And one thing you see here, this point here shows in which direction the robot is thinking to fly to. So this is a computed optimal direction to go, and it also decides for that. And you can see once it arrives here, which is a very tricky area, which is very risky, it is this agent is programmed not to go towards this one. So if I let it run, you will see that it arrives here, and it knows that he has to get the point, but at this point he decides, no, it is too risky to go here, so it's not going towards that point of interest. Now it goes this direction with the hope that it gets through this area, and again here you see that it changes its decision and goes back, and actually if I make it faster, it will never go inside to get the point. Of course, the other option would be that we make it very aggressive. We give it the weight. So as a programmer, I am giving the weight to the agent. And of course, here it will go through. And by the way, this is one of the robots with exact sensory values and censored everything that we have actually in the lab. It actually simulates the robot quite well. And of course, we can now try to change it. And what we do is that we let the robot learn and adapt itself to make the decision on its own without us interfering and giving the predefined behavior. And what you can see here in the simulation, you can't see it quite well, but this point of interest is much closer. So it has to go first to this point of interest and then to get the other one. It goes here, and the moment it sees that it's very tricky here at this point, it changes its mind and it doesn't go there. It goes, it wants to get the other point of interest. Oh, sorry, so it goes there and then goes back. And let me do it. And then here it gets this point. And at this point, he sees that he still has some battery to fly, and it changes its mind and comes back and gets risky enough to go and grab this point of interest. So such behaviors are actually doable for technical systems. And here is basically a autonomous rolling robot, and we told it that it has to go between the two obstacles, and it just goes through. But this shows how the technical systems, I mean, these robotic systems, they have so many mistakes in their failures, in their movements, that it's very difficult to have fully autonomous robot that is capable of also having perfect movement. And still here we can see that the decision-making ability works quite well on such systems. Now the question is, these systems are never alone. There are many other systems around them. So the question is if we can have collective decision-making, if it is better than individual decision-making, and if we can combine them together. And it opens a whole bunch of research questions that actually I'm very much interested in. I'm actually very interested in collective learning, collective decision-making. You might know it as swarm intelligence, but once it comes to decision-making, it gets very, very interesting. So what is that? I don't know if you have heard about that, but for example, an example for that is collective search. So you have many robots, very, very small ones. Actually, these I found it in internet, just put it here, but we have this rolling swarm that you just saw one of them, or we have other platforms also in my lab. And collective search, how does it work? You have a search space. Usually it is a two-dimensional space. If you have flying robots, you can have 3 dimensions. And you want them to collectively look for K point of interest. So for example, if you have a room and you want to look for points with the highest temperature, if there is a fire, for example, or if you have a room with toxic material like radioactivity and so on, you want to find those points. So this is a collective search. So if you would have had one robot, it would go on just randomly walking to find that point. But if you have a set of many robots, they can find it actually much faster and much more efficient in many sense. So what happens is that, so you have basically mathematically saying you have K point of interest, and you want to, the robots find a point that has the minimum value, let's say in terms of, or maximum value in terms of temperature. So F would be the temperature value, or in this case would be maximum, not minimum, or maximum in radioactivity. This would be again maximum here. And there are many points that you want to find. So how does it work? It's very simple. So you have these robots here, and each of them has a position. They start from an initial position somewhere, which is probably not the point of interest. And then they try to move, and every time they move, they look where are the others, and they have information exchange. And then they go towards the one that has a better information than the person that itself. And in this way, they are moving towards the best in their local neighborhood. And then together they can go probably to find those points of interest. So basically you have 2 equations. I don't want to go towards the equations, especially now it's a little bit late, but I just show you how it might work. So basically each of these robots is looking for a leader. The leader is the one that is better than this robot. So basically they look at their neighborhood and they select one of them which is better, and they go towards that. And this is selecting a leader. You can have also a fully connected network that you find the best in the entire swarm and you follow that one. And the equation looks like this. So you have, you basically, a robot has a position X at time T. It adds another velocity to it, which gives a new position for that robot. And the velocity depends on some old values that it had. And this term here, global best, is the one which is selecting the leader. So you look for the one that has the position of the one that is better than you, and you try to basically have an attraction function towards that to go towards this. And this the third part is some sort of personal memory that they usually go also towards their own best achieved position. So now knowing this, so this is a video that you can see, it's actually a GIF file, it's not a video. You can see how a swarm is trying to find these 2 points, the crosses that are not known to them. And in this way, so they basically, it depends on the neighborhood topology we define, they can find these 2 points. You can see how many movements are here, actually. If you want to implement these with robotic systems, I mean, flying robots, you can't do it, first of all, because they are having collisions. And second of all, they are moving a lot and a lot of energy consumption. So now another example for collective decision-making would be something which I call it collective perception. And so imagine you have many robots in this room. It's a 2-dimensional room, and they are moving from one point to the other. And at the end, they have to decide which percentage of the room is, the majority is black or white. So they only have to come up with the option, is it a room is black, or the percentage, maximum large percentage is black or white. And what they do is that, let me run this. So they walk here, and they basically have their own opinion, is for example black, and then they exchange information with the others. And if the others, they say yes, this is the black, then they stay to black. And if the majority says white, they change their opinion. And at the end, the swarm comes up with some common behavior, which we call it a collective perception. It's a collective decision making in a way. So basically, every individual moves randomly in the environment. It could be a levee walk, random walk, or whatever, and they gather the information. And basically, yeah, I can finish the video, and you can see they can find the. So black is. Zoom is not so, but so anyway, they find the white percentage is higher. So at the end, they all turn to believe that white is larger. So now I want to give them individual decision-making capability. So now I tell them, no, don't follow the swarm like an idiot. So you have to think about your own options as well. And if you do that, that will be very nice. So the question is how individual decisions influence a collective. So you have the collective that is making the decision. Now you have one that is doing all sorts of thinking. I'm not following the collective, but I want to also think, make a decision on my own. For that, I make something which we call the individual decision making in collective search. So basically, where I was saying about talking about the leader selection. Now we say don't follow everyone in the best in your neighborhood, but you evaluate your neighborhood. So this is in the brain of one individual. The brain of individual, you have your neighbors. These are all your neighbors that you categorize them in terms of cost and the profit that you have. Usually in the normal one that I showed you, they would select this one. This one has this minus of profit. So it means that it is the best one that I would follow in my neighborhood. Now I will give them the capability that they also follow someone who is not the best, but in terms of energy time that I need to go there is better. Or you could also select any of them in between. So I give them the capability to make a decision, not just to follow like a blind person. And for that, you can have an adaptive approach. Basically, the amount of the decision is how much they have energy left. So if the robot has a lot of energy to move, should go probably to the one that is the far and is giving a lot of profit. But if your robot doesn't have enough energy, probably should not move that, make long movements, but smaller movements. At least it can help the swarm to go forward. And if you do that, here you see the video. We have one default here where this, and they are supposed to find a point here in the middle. And then here you have the decision makers. They also have to find a point here. You see the movements of decision makers looks very weird. I mean, they're stopping sometime and then they make a decision, where these ones, the default one, they are just moving randomly. And you can also see that here is the best, how the swarm is moving. The red ones are the default ones and the blue ones are the decision makers. And here you see amount of energy consumption that they have. And of course you see energy consumption is higher for the red ones, the default one, because they're moving a lot. And these ones are quite lazy because they are saving energy. You can see that they're still not that bad as them. and they are actually helping the swarm to find the optimal solution. There is another example here. Again, you see here how the decision makers are moving like a worm, and here they are randomly moving, and you can also see the red ones. They have a lot of energy consumption actually, and you can also observe here the movement that they have. These are basically not moving; they're lazier because they say I might not move if it is not bringing me enough profit. So that's why they stop. And then once there is one that is far enough, they just move to that person, to that swarm member to work. You can also do a lot of more settings. I don't want to take time. Actually, I'm talking a lot at the moment, so I might skip that. But also, for example, if you have flying robots, you can have also robots that they actually are supposed to go to a point. Maybe I can show you here. The robots have to go to this point, but here, if you have a robot which is here, has a lot of wind against. So if it moves this direction, it is very bad in terms of energy consumption. And so if we give them the capability to make a decision, you see here that they are actually not bad. They follow basically, I have another video, maybe this is even better. So you see here, the decision makers, they follow certain roads. Basically, they try to find the best, they are intelligent, so they try to find the best way how to fly with the wind to save some energy. Of course, if you would have had the wind like this, which probably never exists, who has the vector field like that? But if you do it this way, you see that, by the way, the decision makers are the pink ones. You see that the decision makers cannot find a point of interest which would be located here. And this means that sometimes intelligent behavior might not work if you have really a random environment. So. And of course, you can do even more. You can let them learn their behavior, which is even much nicer. For that, you use the approach called genetic programming. And here they have learned their movement. So we didn't tell them how to do that. They are learning that themselves using this genetic programming. And again, here is the point of interest. And what we found out was, for example, those who are going against the wind. You see here the vector fields showing the wind. They have found a very nice way, a zigzag way. And it's very, if you're a sailor, I'm not a sailor, but those who are sailors, they say that exactly when you sail and go against the wind, you do a zigzag movement. And these individuals who are going against the movement, they found this behavior. The same holds also for these ones. And those who are going with the wind, they go actually straight ahead. So this is very nice intelligent behavior that they can actually learn to, they learn how to make a decision. And the decision is, should I go the best direction? So it would be like, should I go this straight ahead, or should I save energy and find a better way to go? So actually incorporating individual decision-making in a collective, it helps to even be more efficient in such systems. And there is a whole bunch of things that you can talk about, like individuality and collectivity. And the question that I still don't have an answer for that is that how many of the individuals in a swarm, in a collective, should be like selfish ones and take their own way to go, and how many should be following the swarm. So this is one of the research questions that we still need to work on, and how we can influence the collective decision making. This would be great, you know, if we can influence the collective decision making, we could actually influence a lot of, like, even opinions of the human being. We could go in towards the elections and say how we can manipulate people to come up with a better decision. Of course, I'm not expert in that area. I'm working on simple agents and robotic systems. And one simple thing that you can, we know from nature, they also do multi-criteria decision making. And we tried to replicate one of the experiments done by Ian Cousin. And what he did was he had this sort of zebrafish. Zebrafish, apparently they can train, they can actually move, can be trained to learn certain tasks, which I basically didn't know that fish are able to learn anything. Anyway, so they put them in this experiment. The story about this experiment is that you have 3 arms. The arm color and stripe, these are the things that group A is trained for the stripe, so they always go to the stripe. The group B is trained to go to the color. It always goes to the color. And now they put the third one, which is a combination of color and stripe. And then they put the fish here. So if you have only group A, they all end up in the stripe. They don't care about these other two arms. If you have group B, they go to the color. And now if you put A and B together, some of them end up in this consensus arm, which is very interesting. So what is happening there? And Ian Kuzan had a theory about that. And we tried to do a multi-criteria decision making. We said, okay, now the individuals, we give them distance to the target. So they are trained to go to their own target. And we also give an element which is called cohesion. So if I follow the swarm or not, and we let them, if they are lonely in the front, so they don't need to see the swarm, they should go to their own target. But if they are in a swarm, they can make a decision, either follow the swarm or not. And we can actually replicate that. So this is the number of agents. And then here we see the consensus arm, and basically half of the agents end up from group A or B end up in the consensus arm. So it seems that in nature there are sort of decision making. If it is a multi-criteria decision making or not, of course I can't say, but if we use this methodology, we can actually replicate what we see also from nature. You can also influence the decision making, and this is one of those last slides that I want to present. So this is the example that I showed you before. So in this case, it's very tight because we have 48% black, 52% white. It's very difficult, even for human beings, it's very difficult. So now we were thinking how we can influence this decision making, and we came up with the idea, why not? This is very theoretical thing because you can't actually do it in real life. But we said, okay, we use some isomorphic changes. What does it mean? It means that these tiles in the environment, the black and white, we keep the ratio between them, but we reorder them in the environment. So now we have here again 48% and 52%, but with different ordering. And the swarm is now able to find the decision much faster. As you can see here, they are wrong in this side, but they have been converged now to blue, which is the correct one. So it means that you can, by changing the environment, you can actually manipulate the collective decision making. Anyway, so I want to actually end my talk, but before that, I want to tell you that actually you can, as a swarm, you can also learn to solve multi-objective problem with conflict. And I just show you two videos. One of them is we have these robots and we let them we ask them to do a multi-objective task. A multi-objective task is avoid collisions. So they are not allowed to have collisions, but they have to go through the gate. And exactly here in the gate, there is a conflict. So this is a multi-objective task, and every time they don't have a collision, and every time they go through the gate, then it's they get a reward from us. And what thing we did was a human being would design this. This is done by one of my former PhD students. He said he would do these like butterfly movements. And but what the robots found was much more interesting. They found something. We used evolutionary algorithms actually for that. So that's why I call it evolved by evolutionary algorithms. They go to the wall and they follow the wall. That's all what they do. And we did it based on finite state machines. And the finite state machine was very simple. Actually, if you can see that this is evolved by the robots, we have not programmed it before. And they start with empty states and they add states. And every time they meet, they exchange the information and they try to make their finite state machine better and better. So you can see this is the behavior they found. So they are doing sort of wall following, which is very, very clever behavior. And some of them, for example, this one has not reached it. And these two as well, they couldn't. But the rest of the majority actually could learn in a collective way how to reach this behavior, which is very interesting in terms of this multi-objective or multi-criteria aspect. I also duplicated this work just recently. We duplicated the work. We found exactly the same behavior. It's a little bit, I call it like a military group because they are moving in a different way than the other experiment. But here we were working on hidden Markov models and also other aspects. But exactly here you see they have sort of wall following behavior. So at the end, I want to talk about the ethics in AI and decision making. Of course, if you give the machines the ability to make a decision, we have to be also aware of the fact that they could do bad things as well as bad decisions, and who is responsible for that. And there is something which is probably you have heard of it, the trolley problem. Is a thought experiment, is an experiment. And I think it's like what I've heard is like for our computer scientists, the first thing that we write is a hello world program. This is like a hello world program for people studying law. And what they do is that they say, look, if what happens if there is a man here and there is a train going and he is responsible to push this sort of key. And he knows that here this guy is supposed to work, is a worker. So he is the person that once the train comes here, he is not allowed to let the train go here towards this person because he's the predefined worker here and he was supposed to be there to fix something on the road. And then the moment that the train is here, there are 5 people playing here. And they were not supposed to be there. And now this is his decision to send the train either to here and kills 1 person, or sends the train here and kills 5 people. So, and this is a very, I mean, it's, even if it is a thought experiment, it's very difficult. And the same holds also with our computers. I mean, hopefully we will never be like this, but in the autonomous driving cars, whenever I have the roundabout example, exactly, or whenever I'm defining the weights, actually I am touching something very close to this. And the awareness should come to all of us when we talk about decision making. And actually I don't know if you have heard of this, unfortunately I cannot talk to you, but there is a very cute video I want to show you on YouTube that people are thinking about that. So it's not the one that you might so this is a baby and the father is asking him what is the solution for the problem. And you see what the baby is deciding. Yeah. So anyway, I want to come to the conclusion. Decision making is a challenge for both humans and machines. Many decisions that we make, they might influence a lot of upcoming decisions in future, like marriage, for example, and but also now some serious decisions that we are making. And I believe that we can optimize the functionality of autonomous systems by giving them the ability to make decisions at runtime, so change their decisions, change their policies. I think we can do a lot in that direction. And I believe that one thing that I have found in my research is that decision can be influenced by the environment. So you cannot probably influence every single agent, but you can change their environments. And in this way, they can adapt themselves to the environment. And you can basically use artificial dynamics in the environment. And actually, we are using that today. For example, the traffic lights that we have on the road is something that influences changes our environment and is sort of controlling us to stop before the traffic light and move on and so on. So I'd like to come at the end of the talk, and I'm very glad to answer your questions. Hello?
Oh, thank you, Sanaz, for your for this interesting talk. And now it's time for question. So, okay, I can proceed. So first question is this one. Hello, I have a question. May the system have some sort of memory and take a different decision according to the previous history?
Yeah, so that is actually one thing we could do. But to keep that memory is very nice. And this is actually done also in reinforcement learning or also Monte Carlo three-stage approach. You sometimes want to use the memory, but sometimes you want to do exploration. So like you don't want, like the cat and the mouse, you can always use your memory and take the best possible option that you had before. But in certain scenarios, you want to also explore to find other options. And that would be something that you could also consider, not always follow the memory, but also do these sort of explorative decision.
Okay, thank you.
I hope I could answer. I can't communicate.
Okay, yes. So we have another question, and here we go. So can multi-criteria decision-making be applied to legal and medical fields? Is there any ethical issues of obstructing this possibility?
This is a very good question. Actually, I have a project myself now that we work on the pandemic and multi-criteria decision-making. It's not really in medical, but yeah, in that direction. Yes, you need to have, there are many ethical issues, and we write the algorithms, and we should also think of being responsible for the ethical issues as well, even if we don't have any idea about ethical issues, to be very, very honest, as a computer scientist, electrical engineer. But still, we should be aware of the fact that there are. So if you write multi-criteria decision-making, the good thing about multi-criteria decision-making is that we give the alternatives, and the politicians or who is the decision maker, like for example, the cancer treatment, we can give several alternatives and tell them, look, these are all optimal, and now you can decide what to take. That is actually, this is something that we as designers, we can give the responsibility to others. For machines is rather different, and we have to take the responsibility as well. No?
Okay, perfect. So next one is, do you think multi-criteria decision-making may help in diminishing the impact of prejudice and stereotype, for example, in legal trials and or when hiring staff?
Well, it's very difficult to answer this question to me. Well, to have different, but definitely the multi-criteria decision making, when you obtain several alternatives, it definitely helps to come out of this very narrow mind. So you see the alternatives that you have, and then you can basically compare them with each other and make a decision in a very better way than only having one optimal thing and only going for that and being so fixed to that. But this is a very good question. I don't know if I have answered your question. Whoever asked, please write it in the comments, and I can probably, or write me an email and we can have a discussion on that.
Okay, thank you. Next question. So thank you for presentation again. The question is, who will take responsibility for wrong choices that can cause damage to materials or people?
Yeah, this is a good question. This is what I said. I don't know. Well, for driving, autonomous driving cars, there people are talking about if, for example, the companies are going to take the responsibility. You know, if you put this responsibility to the programmer, no one wants to program. So the question is if the companies are going to take the responsibility. And this is one of the things, that's why autonomous driving car might not come as fast as we all think, because of all these legal issues. And also the question is if the driver is responsible, if the program is responsible, if the company that's producing the car is responsible. And I think what comes in future is, it's my personal opinion, I could be wrong, but I think in future it's not the matter of who has the car with the best motor or best PS or whatever they are called, but this is like who has the car with the best programmer, because the intelligent behavior is like entering a roundabout. If I have a car that had a very difficult programmer and I can't go through this critical situation or a crossroad, these are critical situations for such autonomous systems. And if I had a good programmer, then my car is very intelligent, so I could be faster. And then that car would have been very expensive, and not anymore something like if that car had a better designer in terms of motor or interior design and so on. That would be definitely challenging in the future to see what happens actually. Yeah.
Thank you. Next question. Here we go. You have mentioned the possibility to use collective decision-making experiments in order to understand how to manipulate the public opinion. Are you aware of any such experiments? Do you see any potential in helping the public make more mindful decisions and not being easily manipulated?
Yeah, so I've not done myself so many things in that direction. I have done some experiments with humans, 2015, 2017, and several times actually. And I put some people on a tennis field, and I gave them t-shirts and put some cameras and stuff. Sort them yourself in terms of colors, sort them yourself in terms of like t-shirt colors of the t-shirt and so on. This is another story, but there are people people working on those social stuff for many years. There is a professor at ETH Zurich, Dirk Helbig. He's working on so like human being, but he's looking at the human being from the top, like we call it macroscopic. So you look at the flow of people going, the pedestrians, for example, going in a certain environment. There are also people working on social decisions, and they work on the election. For example, one of those very famous research topics was then in France, I don't know when, 80s or 90s, I think 80s, Jacques Chirac won the presidential office. So he was the president. He was a minority. He was minority, like in the beginning, he was 25% minority. And he, at the end, won the election. So many of these social scientists are looking at the behavior of people. And so it's something like the collective perception one, that you move and then you see the other people and they convince you about their decision. So the same holds also in election. And there are people working on that. And I think this is now just something that I cannot prove, but I think people are also doing in the elections everywhere. You know, you can manipulate people by showing them different advertisements or in different environments. So for example, in the United States, there are different neighborhoods, right? So the states, and every state is sort of like, you can manipulate one state and they can talk to the others and so on. So there are so many things that people can do. And thankfully, I work with technical systems and robots. So we manipulate our robots and they are faster and save energy. We don't work with human being. Is a very complicated thing to do. Yeah, but there's market there. If you are interested, you can go and earn some money actually.
Okay, thank you for the answer. And now the last question. Here we go. There are classical examples of complex behavior emerging from simple rules, like Conway's game of life. Is there any chance of obtaining complex and effective decision-making from simple rules?
Yeah, so this is what we are doing. So like all this game of life is, or cellular automata, these are the origins of the ideas that we have in collective decision making. And basically they said that if you have simple individuals, simple rules, and only local interactions, you can achieve something which is called emergence behavior. And the emergence behavior is very interesting because if you ask individuals, they are not aware of the fact that they are doing that global intelligent behavior. Like imagine you have ants, they are very simple. If you would have had one ant here would walk on the table and be like very simple, stupid, doing nothing. But once you have many of them, you put them together, they build an ant road. We see it whenever we go to a forest, we see ants walking behind each other. This is a very intelligent behavior. And the idea is that if you ask one of those ants, do you know you are making that beautiful ant road? Or sometimes they make bridges. They do actually very nice stuff. If you ask one of them, they don't know anything. But once they get together, they build that very complex, intelligent behavior. So these are the things that we use also in this decision-making aspect. But as you see, we work on very abstract. Still, the research community is not that far to make very complicated behaviors. You can use these methodologies, for example, self-driving cars, and say, okay, what happens in future if you have self-driving cars? We don't need to have a traffic light, because traffic light is like for us human being to see it is green or black, red or yellow. And so how can they come out of like traffic, or how can cars go through the crossings and so on? And for that, you can use the methodologies based on those collective decision making and emergent behaviors and so on.
Okay, thank you.
You're
Thank
welcome.
you for answering. And now we would like to give you a certificate for your nice talk, and to thank you to be with us today. So typically we give a certificate of appreciation, but in person. But given the current situation, we cannot give to you by hand. So we will send you by email a copy of this certificate that actually our attendants are seeing printed on the screen. So thank you very much.
Thank you so much. My pleasure being here, and I wish I could see you in person, all of you, also those who are on YouTube, and I enjoyed answering the questions. Thank you so much.
Thank you, Sanaz. And now I would like to thank also the Women in Engineering Italy section and Vivum Engineers for their advertising, for promoting the event. All the people involved in the organization of this event, our virtual guests, and the student branch of Polytechnic of Turin, and the IEEE Computational Intelligence Society for this program about distinguished lecturer. Thank you very much, and we hope all of you enjoyed our talk, and see you soon.
See you.
Bye.
Goodbye. Bye-bye.